Hello, welcome to another module in this massive open online course. So, we are looking at MIMO beamforming, how to design the optimal transmit and receive beamformers in a multiple input multiple output wireless communication system. So, let us continue our discussion. So, what we want to look at is we want to look at MIMO beamforming, and we have said after combining with U bar Hermitian, U bar is that receive beamformer, we have U bar Hermitian H V bar times X plus U bar Hermitian noise. This is the noise vector. Now, what we have to do is this is your receive beamformer and U bar and V bar is the transmit beamformer, and we want to design this to jointly design transmit and receive beamformers to maximize SNR. First, what we will do is we will set H V bar, we will set this quantity equal to H bar, and now you will observe something interesting. This becomes U bar Hermitian H bar into X plus U bar Hermitian times N bar. Now, if you see this H bar, this effectively becomes a single input multiple output system. By setting H V bar equal to H bar, this effectively becoming a CMOS system or a simply multiple receive antenna system, for which we already know the optimal beamformer effectively becomes your multiple RX antenna system. And once it becomes an RX antenna system, what you have is that this is equal to, now therefore, now you know what is the optimal beamformer U bar. The optimal beamformer U bar for this multiple antenna system, optimal RX beamformer is the maximal ratio combiner, that is U bar equals H bar divided by norm H bar, okay, and therefore, we know this is the maximal ratio combiner, this is your optimal beamformer, maximal this is the maximal ratio combiner, and the output SNR of the maximal ratio combiner is given as norm H bar square P over sigma square. Remember, P is the transmit power, sigma is the noise power. So, this quantity is constant, P over sigma square, okay, because P is the transmit power, sigma square is the noise power, implies that we have to maximize norm H bar square. So, to maximize the SNR, we have to maximize norm H bar square, okay. So, in order to maximize SNR, so that is the optimization problem, maximize, or let us say maximize output SNR, we have to maximize norm H bar square, but H bar equals we have seen H bar equals H times V bar or capital H times V bar. So, H bar equals H times V bar, which basically implies, substituting this, we have to maximize norm H times V bar square, which is basically norm H times V bar square. And what is norm H times V bar square? H times V bar square is the vector Hermitian itself for a complex vector, which is basically V bar Hermitian H Hermitian H into V bar, which is equal to V bar Hermitian G into V bar. So, we have to maximize this quantity, where what is G? G equals H Hermitian H. G equals H Hermitian H, and we have to maximize. So, optimization problem, so the net optimization problem becomes maximize V Hermitian GV subject to the constraint. Remember, the constraint is still there, unit norm constraint, that is the transmit beamformer, energy of the transmit beamformer or power of the transmit beamformer, norm V bar is less than or equal to 1. So, this is the resulting problem for optimal beamformer. Alright, we have substituted H bar equals H times V bar, and from that you derive this in terms of the optimal, this optimization problem for the optimal beamformer. And now just to simplify it, what I am going to do is I am going to assume real vector. So, I am going to replace this Hermitian by transpose. So, I am going to say, to simplify, consider real vector. So, this becomes V bar transpose G V bar subject to the constraint norm V bar less than 1 or norm V bar square less than or equal to 1. Both these constraints are equivalent. And observe that interestingly, this is a non-convex problem. This is one of the few and very interesting non-convex problems, because if you look at this, V bar transpose G V bar is a convex function, correct. However, we are maximizing it, we are not minimizing. Remember, standard form convex optimization problem, you have a convex objective but you are minimizing it. Here a convex objective you are maximizing. So, the problem is a non-convex problem, although the objective is convex, because you are maximizing it, it's a non-convex. In fact, if you minimize it, you have to take the minimum and minimize it, but once you take the minimum, the convex objective becomes a concave objective, and therefore it is a non-convex problem. Okay. And therefore, it is because G is a positive semi-definite matrix, G equals a PSD matrix, and V bar transpose G V bar equals convex. However, what you are doing is you are minimizing a convex objective, you are performing minimization over a convex objective function implies that this is non-convex, and therefore, now what we will do is we will form the Lagrangian, the same thing that we have done before, that is f of V bar comma lambda. Remember, you have the objective V bar transpose G V bar plus lambda times 1 minus norm V bar square, objective plus eigen plus Lagrange multiplier times constraint. This is equal to V bar transpose G V bar plus lambda times 1 minus V bar transpose V bar. Now, differentiate it, take its gradient with respect to V bar, this V bar transpose G V bar twice G V bar plus the gradient of lambda with respect to V bar is 0 minus lambda derivative of V bar transpose V bar is twice V bar, minus twice V bar, or in fact minus twice lambda V bar, this is equal to 0. Now, if you solve it, the 2's cancel, and therefore, this implies that G V bar equals lambda times V bar, and then you observe something very interesting. What you observe is that G V bar equals lambda V bar, and recall, you have already seen this kind of equation, this equation before, this is nothing but the definition of the eigenvector of G. That is, any vector V bar which satisfies this property, that is G times V bar vector equals simply a scaling factor lambda times V bar. V bar is the eigenvector and lambda is the eigenvalue. And so that is the interesting property. So what this shows is that the optimal transmit vector V bar equals eigenvalue of G equals, now you can write H Hermitian H, okay, that was just for simplicity. So this is the eigenvector of H Hermitian H, okay, this is an eigenvector of H Hermitian H, right, but correct, right. So this has many eigenvalues. Now which eigenvalue, now how to find which eigenvalue? Or you can say how to find the Lagrange multiplier lambda. So we can say that this will be V transpose G V bar. Now G V bar equals lambda V bar, so this becomes V transpose lambda into V bar, which is lambda times V transpose V bar, which is lambda times norm V bar square, but norm V bar square equal to 1, so this becomes lambda. So this is lambda and we want to maximize this. We want to maximize V bar transpose G V bar, implies choose the maximum lambda or choose eigenvector corresponding to maximum lambda eigenvalue of H Hermitian H. That is, let us say we can denote this by lambda max of G, which is lambda max of H Hermitian H. G is H Hermitian H. And that is something that is extremely interesting. What you have, what it says is the transmit beamformer H Hermitian H corresponds to the max eigenvalue corresponding to the maximum eigenvector of H Hermitian H. That is the transmit beamformer V bar, unit norm transmit beamformer V bar, which maximizes the SNR at the receiver. So choose V bar. Unit norm, choose V bar equals unit norm eigenvector corresponding to maximum eigenvalue of corresponding to the maximum eigenvalue of H Hermitian H. That is the interesting aspect. This is also termed, this eigenvector corresponding to the largest eigenvalue, this is also termed as the principal eigenvector. Transmit beamformer V Hermitian, transmit beamformer V bar is the principal eigenvector corresponding to H Hermitian H. Now what about U bar, the receive beamformer? Remember U bar receive beamformer, we still have to find that, that is H V bar divided by norm H V bar. Now this norm is simply a normalization, so for the time being ignore this, that U tilde equals H V bar. Now look at this, now perform H Hermitian U tilde equals H Hermitian into H V bar, but V bar is eigenvector of H Hermitian H, correct. So this will become H, now look at this, H Hermitian H V bar is equal to lambda V bar. So this is lambda times H V bar, but H V bar is U tilde. So what we have here is, we have showed something very interesting, H Hermitian U tilde equals lambda times U tilde implies U tilde is the eigen, that is the receive beamformer U tilde is the eigenvector of the matrix H Hermitian, and that is something that is interesting. U tilde, again you can say U tilde, or now you can say U tilde equals principal eigenvector of H Hermitian. That is eigenvector corresponding to largest eigenvalue of H Hermitian, and now U bar is simply U tilde divided by norm of U tilde, which is principal eigenvector with unit norm. Remember, you can simply scale the eigenvector by any quantity, it will still be an eigenvector. So, this is the, you can say, principal eigenvector of H Hermitian with this is the principal eigenvector of H Hermitian with unit norm. Okay, great. And therefore, that basically gives us both the transmit and receive beamformers, and we have very interesting expressions for them. The transmit beamformer U bar, optimal transmit beamformer. So, to summarize, you have the MIMO beamforming problem, y bar equals h x bar plus n bar, x bar equals, so this is v bar times x plus n bar, that is your y bar, and at the receiver you perform U bar Hermitian v bar y bar, which is U bar Hermitian h v bar x plus U bar Hermitian n bar. And remember, what you are doing here is, as I already told you, you have to perform beamforming at both the ends in the MIMO system. So, you have the transmitter, you have the receiver, you are transmitting from the transmitter in a particular direction. At the receiver, you are also collecting, or you are also processing the signal, you are steering the receive antenna array in a particular direction. So, this is basically your transmit steering. Remember, this is all electronic steering, so you do not need to physically steer, and this is your receive steering. And U bar equals eigenvector of H Hermitian corresponding to largest eigenvalue, or principal H Hermitian, and V bar equals principal eigenvector of H Hermitian. Now, later what we will see is, we will see what is known as the singular value decomposition of the channel matrix, and it will turn out that U bar and V bar are in fact the dominant left singular and right. U bar is the dominant left singular vector, which means singular vector corresponding to the largest singular value, and similarly V bar is the dominant right singular vector corresponding to the largest singular value. In fact, we will see later, that is U bar comma V bar are the dominant singular, and this is a key phrase, not eigenvectors but singular vectors of H from the SVD, what we call, not the EVD, from the SVD, which is called the singular value decomposition. From the singular value decomposition, and further from the singular value decomposition, and remember dominant singular values means corresponding to largest singular value. Dominant singular vector means corresponding to the largest singular value. And in this context also we have seen a very interesting optimization problem, that is, if you take a positive semi-definite matrix x bar transpose Ax, maximize subject to the constraint norm x bar equal to 1 or norm x bar less than or equal to 1, then x bar equals principal eigenvector provided A is positive semi-definite. Remember, x bar transpose x, provided A is PSD, positive semi-definite matrix. Provided x bar is a positive semi-definite matrix, this is a principal eigenvector of A, that is the maximum x bar. Now, similarly, if you minimize, now this is another interesting analog. Now, this problem is convex, minimize x bar transpose x bar such that norm x bar, of course, this is not convex again in the sense that the constraint is not convex, norm x bar greater than or equal to 1, then x bar equals eigenvector corresponding to smallest eigenvalue. So, there is an analogous problem, eigenvector corresponding to x bar equals eigenvector corresponding to the smallest eigenvalue. And therefore, this is a very interesting application as we have seen here, that is basically with respect to beam forming in a MIMO system to determine the optimal transmit and the unit norm transmit and receive beamformers, which are given as V bar. The optimal transmit beamformer is the principal eigenvector of H Hermitian H, or you can also say the dominant left singular vector of H, and U bar is the principal eigenvector of H Hermitian, that is the dominant left singular vector of H, the channel matrix. H is the channel matrix of the MIMO wireless system. Alright. So, with this interesting observation or this after completing this interesting example, we will stop here and we will continue in the subsequent modules. Thank you very much.